1 over square root of 2 times, right? I'm going to use S for sigma times pi. And then e to the negative x minus, I'm going to put mu, or no, I'll just do u. Okay, u squared, and then all over 2 times s squared. And I don't know why it didn't do square root. Let me try this again. SQRT. There we go. 2s times pi. Okay, there we go. And now I can control the value of, okay, y'all see that? See that graph right there? Goes in both directions forever. I'm going to change the value of the u, all right? Look what happens. If I change the value of sigma, look what happens. Oh, shit. Y'all see that? Okay. What this is known as is the standard normal distribution, or better known as a bell curve. You've heard of the bell curve before? So the way the standard normal distribution works is this, is that what we have discovered is that given any random variable, if you look at any random variable, the distribution, what we call the probability density distribution, should look like this. Let me give you an example. Let's say that I take a bunch of people, okay, 10,000 people, and I start measuring how tall they are, all right? How tall those people are. And let's do this in feet. All right, so let's say here's like 5 foot, right? And then what, we're going to have a lot of people 5 feet? Let's say this is count how many we have, right? How many? How many we have? We should have a lot of people in this range. If this is, let's say 6 foot, let's say this is 7 foot, let's say this is 4 foot and 3 foot, right? What we should expect to see is a lot of people in this range, right? And then what happens is you start to tail out, right? Like this. Start to tail out. That is what we call a standard normal distribution. When I give a test, right, what I should see is a standard normal distribution. I should see an average in the middle, and then I should see students above the average and below the average, right? So this right here, this number right here is the U. That's your average. And then the standard deviation is the S. That's how far away people are from the average. So look at right here. If I change my standard deviation, my S, look at that. I'm making S small. What does that mean? Everybody lies really close to the average, right? If S is small, then everyone lies really, really close to the average. If I have a large standard deviation, then the opposite's going to happen, right? Large standard deviation. This is like, you never want this sort of situation, right? And at least not for test scores, right? For test scores, you don't want that. That means everyone's all over the place, right? You got a bunch of people way out here, a bunch of people way over there. All right, so this is one of the most important formulas in statistics because it's our bell curve. But I need to explain something else before I get to what I want to really get to. So let's take a step back. Okay, I'll leave this up here. I want us to look at a certain scenario here. And by the way, what I'm showing you right here is not going to be tested. This is more just so you understand what this function is and like why it's important, these types of things. Let's say that I have a box over here, okay? And in this box, I'm going to put just some random cards in here. I'll put, let's see, a blue card, 2 blue cards, 3 blue cards there. And let me put a couple of red cards in here. Red, 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 another red. And then let me put, I don't have a green. Is there a green around here? See a green? Oh, I have a green. Let me just put 1 green card in here, okay? All right, so people are going to close their eyes and reach in here and grab a card, right? So what I want to do here is I want to first You're only going to draw one card, okay? One card. So this is going to be the outcome of you drawing that one card. And this is going to be the probability of that happening. So when I draw a card, how many different outcomes are possible if I just draw one card? Yes, 3, but when I pull it, I have what, either a... Yes, so 3, yes. So I can either have what, a green, I can get a red, or I can get a blue, right? Those are the 3 possible outcomes. What is the probability of each one? So what's the probability that I draw a green card? What is it though? 1 out of 9. So let's say that right here, I'm going to put a box here. I'm going to say that that's 1 out of 9. Okay, that box. I'm going to say the height of that box is 1 out of 9. Okay, now the red. What's the probability of getting red? 4 out of 9? It's up here, isn't it, like that? 4 out of 9? What's the probability of getting, was it 5? Oh, it's 5, yeah. Sorry, 5 out of 9. And then what about the blue? 3 out of 9. So something like this, right? 3 out of 9. Do y'all see that that's one way I could represent those probabilities? Yeah? Now, let me add one more thing. What if I tell you that I want to make this rectangle have a width of 1, that rectangle a width of 1, this rectangle a width of 1? Then what's the area of that rectangle? 1/9. What's the area of that rectangle? 5/9. What's the area of that rectangle? 3/9. What's the total area of all the rectangles? Total them all up. What do you get? You get 1, don't you? The total area, that plus that is 1. And that makes sense because what these areas adding up to 1 means that the sum of all of the possible outcomes, the probability of all the outcomes is 100%, right? If you say, okay, what's the probability of getting a green? Well, 1 out of 9. What's the probability of getting a red? Well, 5 out of 9. What's the probability of getting blue? 3 out of 9. What's the probability of any one of these what's the sum of all the probabilities? The area of that, right? Which is 1. 100% certain that you're either going to get a green, a red, or a blue, right? You'll still follow that? Okay, let's take another example. So I go off on this. Sometimes I wonder why I go on this, but I think it's important to see. I want to take another example here. Let's say that, we have so many, let's do this. This will be, I don't know if it's going to be fun, but we're going to do a poll here, okay? There are 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe 26. Okay. We're going to do here siblings, okay? Siblings. How do you spell it? S-I-B-B? Is it BB? Yeah. It's 1B? Really? Okay. All right, so let's do a quick, we're going to do a quick count first. How many of you, and if you're uncomfortable with this, just lie to me, okay? Okay, so how many of you have 0 siblings? How many of you have 0 siblings? 1, 2. Okay, 2. So 2 have 0. Okay, 1 sibling? 1, 2, 3, 4, 5, 6, 7, 8. 8. So 8 have 1 sibling. 2 siblings. 4, 5, 6, 7, 8. Me too. 9. 3. 2. 4. 3. 5. 6. 7, 8. Anyone higher? Yeah. What do you got? 9? Oh my gosh, okay. So 5, 6, 7, 8, 9. Okay, and you 1, right? Just you. No one else, right? 9 siblings. Okay, good. How many do we have total here? It's 8, 19, 20. There's 25 here, okay? 25. So what is, going off of this, what's the probability for this classroom, right? If I pick someone, what's the probability that they have no siblings? 2 out of 25. So if I do a rectangle, right, 2 out of 25. What's the probability of having one sibling? 8 out of 25, right? 8 out of 25. If I pick somebody, what's the probability that they have two siblings? 9 out of 25, right? 3 siblings? 2, so like this, 2 out of 25. That's for 3. All right, 4. 3 out of 25, right? 3 out of 25, that's for 4. And then 5, 6, 7, 8, 9. 9 over here, we have 1 out of 25, and these are what? 0, right? What is the sum of the total areas of these? 25 out of 25, which is 1, right? No matter how you ever do this, for any measurement like this, if you put all the outcomes there and you draw boxes with widths of 1, the sum of the areas will be 1 or 100%. Okay? Now, we're not going to mess it up. We're not going to ask. You don't happen to have 9 siblings, do you? Never mind. All right. Okay. We're going to do one more experiment. You ready? This is going to be where you start to see, okay. Why do we need integrals? Why do we need integrals? I want to do something different. Let's now do weights. Okay, now look, I'm not going to ask you for your weight, all right? However, where do I begin? Like if I were to say, okay, how many of you weigh, right? If I say, how many of you weigh 160 pounds? Well, maybe you don't weigh 160 pounds. Maybe you weigh 160.2 pounds, right? Or maybe you weigh 162.256 pounds, right? Like there's different precision to measuring that, right? When I say number of siblings, you only have whole number answers for me, right? But if I ask for the weight of something, it actually depends on how accurate that scale is. Of course, we could round, right? We could round. But other things in the real world, like if you're trying to measure the length of something, right? It depends on your instrument that you're measuring with, how accurate it is. So when I put these weights here, what I could say is probably we go like, 0 here, and then if this is 1, right? Then all I know is that whatever my probabilities are, when I look at when I graph these, instead of it being rectangles like this, it's going to be a curve like this, okay? It's going to be a curve. Because you have not only the whole numbers, but you have everything in between as well. So you can't draw rectangles anymore. So what you do is you just draw a curve, and then what do we know? Is that the sum of all of the probability, just like the sum of all these areas, has to add up to be 1. This total area under here has to be 1 in order for this to be accurate in terms of what we call probability. This is called a probability density function. It's just a graphical representation of all the probabilities. So let me just try and explain. Let's say that this was 160 pounds. And let's say that I told you that that was 35.35. So at 160 pounds, this is 0.35. So there's about a 35% chance that somebody weighs 160 pounds, right? So what we do when we have this scenario is instead of looking at boxes, we look at the total function. And instead of asking, hey, what's the probability of someone being 160? You say, what's the probability of someone being between 160 and 165? And then you have to calculate that area. That area is like what these boxes used to be, but now do you see it's not a box? So how do you calculate that area? Use an integral, okay? Use an integral to do it. So, backing up, what's so important about this function? If you integrate this function from -infinity to infinity, no matter what you ever pick for sigma, no matter what you ever pick for u, no matter what you ever do, what do you think the answer to this is? 1. 1. Always 1, no matter what. And so that is like the master probability density function because it always gives you an area of 1, so it always gives you a probability density function. So we use it in statistics all the time. Now, unfortunately, this integral is impossible to do for us. Like, we don't have a technique of integration. Not because of all these crazy numbers. Like, if you take this out, right? Take that out. That's just a constant. We could have pulled it out of the integral. This right here, we could ignore. It's a constant. That right there is a quadratic. So basically, this integral really turns out to be like, can you do this? And we look at that, and it seems like maybe we could do that integral, right? We can't. That's not possible. Not until we do chapter 8 in this class, right? And to show you, I'm going to go to Wolfram alpha, and I'm going to ask Wolfram alpha to do it for me. Maybe. Yeah, here we go. I'm going to ask Wolfram alpha to find the antiderivative of e to the negative x squared. And see what it gives me. And what it gives me is 1/2 square root of pi times erf x. And erf x means, does it show it here? I think I went too big there. Erf x means, erf x is the error function. So that's basically Wolfram alpha saying they can't do it. And so there is no way to do this, which is why when people see this this bell curve, they're like, well, why do we have the bell curve? It's such a complicated function, right? Like, how do we integrate it? Well, chapter 8, we will have a way to do it, all right? It's just right now we don't. All right, we're gonna go away from this. All I wanted to do is show you right there, like, where in the real world these improper integrals come into play. It's in statistics when you're trying to figure out probabilities for things that are not whole numbers. When you study things that involve whole numbers like this, number of siblings, I don't know, number of cars you've owned in your life, things like that. I mean, just those are what we call discrete random variables. Discrete meaning that there are finite answers like this. Whenever you deal with something like this is called continuous random variables. And to do that, you have to be able to do integration. You have to be able to do areas under curves. There's actually statistics courses. Anyone here ever taken a statistics course? Yes? Okay. So when you take stats, it's kind of like, I don't know if you've ever, anyone here has ever taken physics, but do you know in physics there's like the non-calculus physics and then the calculus physics, right? Usually it's called like, I don't know, general physics or whatever, and then it's called like technical physics or something like that. Technical physics is like they assume you know how to do derivatives and they assume you know how to do integration and stuff like that. When it comes to statistics, it's the same way. There's regular statistics and then there's calculus-based statistics. If you take calculus-based statistics, then you've got to use the integration to do this stuff. Much, much harder class. All right. Notes. All right. How are we doing on time? 15 minutes. Let me see if this is the last thing here. Yeah. This is the last thing for today. Should have enough time. All right. What we want to show here, we want to show that if you do the integral from 1 to infinity of 1 over x to the p dx, then we can find the answer just by looking at what that p is. The p here stands for power, okay? So the power on the x. If we know the power of p, then we know the answer. So it says here, we need to show that if p is, what? Less than or equal to 1, what will happen? It diverges. And if p is greater than 1, it's going to converge. Converge. Now, I did some examples, right, to start class? Didn't we do this one? That was the very first example I did, right? What's p here? Do y'all see it's in the form that we're looking at up there? What's p here? 2. And did this converge or diverge? Do y'all remember? P was 2. And yes, it did converge. What did it converge to? It converged to 1. We did that problem, right? All right, and then we did another problem where I changed it up and I said, hey, let's go from 1 to infinity. Let's do 1 over x dx. And that's the one where the natural log came in, right? Do y'all see again this is in the same form? What's p here? P is 1 this time, right? P is 1, and it diverged. So it's kind of doing what this is saying, right? Here, if p is less than or equal to 1, it's going to diverge. Well, that's what happened, right? If p was greater than 1, it's going to converge. What we're going to try and do is show that this is true for any p less than or equal to 1 and any p greater than 1. We've only shown it for 2 different examples here, right? We have to show it for all p. So let me show you how you go about doing this. First thing I'm going to do is this. Let's do the integral from 1 to infinity of 1 over x to the p dx. All right, this, just by the definition, is the limit as t goes to infinity of integral from 1 to t of 1 over x to the p dx. Got a lot of letters in here, don't we? Okay, so we're just replacing the infinity with t. We're taking the limit as t goes to infinity. It's 1 over x to the p dx. Now an antiderivative. Right? Now an antiderivative. Now be extremely careful here because this really is x to what power? Negative p. And if you did the power rule on that, right, to do the antiderivative, you'd have to add 1 to this, right? Okay, so let me do that. Let me do it right here. Limit t goes to infinity. So the antiderivative of that be 1 over what? What's out front?
1 over
negative p plus 1, x to the negative p plus 1. Everyone understand we're just doing the power rule on this? Like if this was x squared, we add 1 to the power, we do 1 over 3. Well, here, same thing. All right, now I'm going to take that and I need to evaluate that at 1 and t. I'll come over here. Anyone need clarification on that step? Okay, this is equal to limit t goes to infinity. Okay, bracket, I'm going to have a set of parentheses minus another set of parentheses, fundamental theorem of calculus. Plugging in what first? T for what? T for x, right? T for x. So this is 1 over negative p plus 1, t to the negative p plus 1. And then we plug in what? P plus 1. We plug in 1 for x, right? 1 to the negative p plus 1. A lot of things to keep track of there, right? Now, I see that we potentially have a problem. Do y'all see that we have a problem if p is 1? Do y'all see that if p is 1, we have a problem with what we're doing right now? If p is 1, then this is 0, right? If p is 1, this is 0? Okay, so what I need to do here is I need to put something here and say for p not equal to 1. This is true, right? This should be true as long as p is not 1. If p is 1, we have a different scenario that we have to look at. You ready to take a limit? Let's do this first. What is 1 raised to any power? 1, right? This isn't a limit. This is just the number 1. 1 to any power is 1. And then 1 times that is that, and then minus that, right? So we have minus over here 1 over negative p plus 1. That's what I have here, right? That's a 1, okay, and then it's just these two together. This is the part that's harder. What's happening here is that this is headed to what? Infinity. So we have some number that's getting huge, right? But it's being raised to what power? Negative p plus 1. Right? What happens if I take a number that's getting big and I raise it? What if I raise it to a positive power? It'll still be big, right? A big number to a positive power is still a big number. But what's a big number to a negative power? Getting closer to 0, right? Getting closer. So this depends, right? Doesn't this power dictate what's going to happen to this? This power dictates what's going to happen. If minus p plus 1 is what? Bigger than? Like if it's positive, what's going to happen? It's going to grow to infinity, right? This thing's going to become infinite. But what if that negative p plus 1 is less than or equal to 0? Then it's going to head to what? 0, right? It'll head to 0. And you know what? Let's take the equal out of here. Let's take the equal out of here because we already said p can't be 1, right? P can't be 1 in this whole scenario. So if I put an equal here, then it's possible for p to be 1. I know that not everybody understands what I just put on the board. I know that, and people are not saying anything. So I'm going to go through it again. Imagine you have a number here as t goes to infinity. Imagine you have a number that's getting big. Let's say 1,000,000, right? And you take that number, and let's say that this number here is positive. I don't know, 3. 1,000,000 to the third power is going to be big, right? That's becoming infinitely big. And it doesn't matter what this number is. Even if it was 0.3, that's still going to get big because that number is just growing and growing and growing. And then this just means like you're taking like a root of the number, still going to be big. But if the number up here is negative, now it's 1 over this number, isn't it? 1 over that. And that's going to get small. So that's why if this power up here is bigger than 0, positive, this whole thing is going to grow. And if this thing is less than 0, it's going to go to 0. Okay, so let's look at those two scenarios. What happens if this thing goes to infinity? This right here. If that goes to infinity, if this goes to infinity, what can you tell me about the whole thing? It diverges, right? And if this thing goes to 0, then this thing goes away, right? And all you're left is with this, right? And this is just some number. This is just some number. So it would converge, wouldn't it? It would converge. Okay, solve this inequality. Move this p, add p to both sides, and what would you get? P is less than 1, right? P is less than 1, we diverge. Add p to both sides here, and you get p is greater than 1. P is greater than 1, you converge. All right? What about when p equals 1? We didn't look at that. What if p equals 1? What would this integral be if p equals 1? We did this problem, natural log, right? And what did that do? Diverge or converge? It diverged. So that's why we can put the equal under here. Because if it is 1, it will diverge. Okay, you don't need to know all this. I'm just showing you how we could come up with a formula. Here's what you need to be able to take away from it. Quickly, without giving me an answer, a specific answer, just tell me if this integral converges or diverges. Converge or diverge? What's p? Careful, in the formula, this is p. It's on the bottom already. So p is a half, right? The square root is the half power. So p is a half, converge or diverge? Diverge, right? P is a half, this diverges. Diverges. Okay, what about this? Still diverges. The fact I started at 20 does not change anything, all right? Because this one is doing this. Starting at 1, we're finding this area. And here we're starting where? At 20. But you know what? It's okay. It's just like, you know, if all of this is infinite, right? If this whole thing from 1 to infinity is infinite, then if I cut off a finite part of it, that's still got to be infinite. The infinite is coming from down there, not from a finite piece in the beginning. All right, what if I change the problem? I do this. How are we doing on time? Okay. How about I do this? Let's go 1 to infinity. How about square root of x cubed? Does it converge or diverge? What's p? What's p? 3 over 2, right? If you rewrote this, this is the same as x to the 3/2 power. 3 over 2 is 1.5. 1.5 is bigger than 1. This should be a convergent integral, all right? All right, we're done. Let me just quickly preview what's going to happen next class. Next class, we're going to look at something like this. We're going to do an integral, let's say, from 0 to, I don't know, 4. So it's going to look a lot like what we did last week, right? But in here, we're going to have something like this. And I want you to notice that there's a problem in here. Do y'all see what the problem is? Look at, we're going from 0 to 4, right? Look at that function. What happens at 2? Your function is undefined, right? And so how does that impact things? Do y'all see at 2, if I try to plug 2 in here, we get division by 0? Our function is not defined at 2. So what we have is a discontinuity. When we're looking at our interval, we have a discontinuity on the interval that we're looking. And when you have a discontinuity, you have a problem. You have to deal with it. And that'll be what we do next time. Those are our type 2 improper integrals. Yes?
Say, like, on the integral, when you wrote 1 to infinity, would it
Yep.
be the same if it was negative infinity to infinity?
No, good question. This does not work from negative infinity to infinity because this is not defined at 0. Do you agree with me? If I put 0 here, right, it's division by 0, it's undefined. So I can't go from negative infinity to infinity because at 0 it's undefined. Next class we will work on how to get around that. So this formula only works if it's 1 to, well, actually this should be any constant as long as it's bigger than 0. But the way you'll see it in here is 1 to infinity. Okay, everyone, have a good rest of your day. Remember, a test a week from today. Yeah, homework, good question. Let me bring up that calendar. It's in 2 parts, I believe. Look at it. Where is it? I need to actually look at it. Let me send an email. Because the homework includes both types. We've only done one type. So here's the thing you could do. Look at it. Anything that has infinity, either on top and bottom, do. If it doesn't, don't do it. Yeah.
Thank you.
Yep.
Would that one work if it was a negative infinity on the bottom, negative 1 on top?
Yes, it would.
It would? Okay.
Well, yes. It would be a different setup. You know how we had a piece that remained?